It's a pleasure to welcome today's speaker. It's Ilya Gekhtman from Yale. So he's going to tell us something about the green metric, Ancona inequalities, and the Martin boundary for relatively hyperbolic groups.
Hi, so thanks for inviting me to speak here. So I'm going to talk about joint work with some people with partially with Viktor Gerasimov, Leonid Potykhailo, and Wenyan Yang, and partially with these two gentlemen, and also Mathieu Dussala. Okay, so the object of study here are going to be finitely generated groups. So gamma is going to be a finitely generated group, well, infinite group, and mu is going to be probability measure in gamma. So this measure induces Markov chain on gamma, which is called random walk associated to mu. So the transition probabilities are the probability of going from G to H is mu of G inverse H. And okay, so to this you can associate Green's object called the Green's function as follows. So a path in gamma is a finite sequence and the weight of this path is defined as called omega. So P of gamma as mu of gamma 1, mu of gamma 1 inverse gamma 2, all the way to mu of gamma n minus 1 inverse gamma n. So it's going to be the weight of this path, and the Green's function. Sorry?
This is gamma naught, elements of.
Yeah, so this is just a sequence of elements of gamma, of the group. Finite sequence. And the Green function is defined as, so the arguments are elements of gamma, and is defined as the sum over all path from x to y. So a path, so a sequence of any length starting at x, ending at y, of p of gamma. Okay, so this is called the Green's function. So it is finite yes, so we're always going to have the standing assumption that this semigroup generated by mu is the whole thing. But so this Green's function is finite for all x and y, or equivalently for a single x and y, if and only if the Markov chain P is transient, and well, this means the probability of coming back to a point infinitely many times is 0. But this is true. This is always true unless gamma contains Z or Z2 as a finite index subgroup. Okay. So we're always going to work with the assumption that this Green's function is finite now. So if you only care about Z and Z2, this is not the talk for you. But right. So then the quantity f of xy equals g of xy over g of yy, which is g of xy over g of the identity. It can be interpreted as the probability that sort of mu governed path starting at x ever reaches y. And if you take minus log of that, so this is called, so it's called the Green metric. So I call it the Green metric, even though when the measure is asymmetric, this metric itself is also asymmetric. But it satisfies the triangle inequality and all the other conditions you would want in a metric. So, asymmetric metrics are not such a travesty. Right. So a major theme in sort of geometric group theory and random walk set groups is relating properties of this metric to the geometry of the Cayley graph of the group. So one useful way to do this is with something called the Martin boundary. So the Martin compactification is defined to be the Hora function compactification of of gamma with this metric dg.
You should know that Martin was the best mathematician ever fired from the University of Illinois.
Oh, really?
Yeah.
Okay.
have a speech defect.
Well. So, right, so what's the Horner function compactification? I'm going to write this on the side. So this is something that whenever you have, I guess, so X is a metric space, you can, XD is a metric space. You can embed X into the space of continuous functions of X. So you fix a base point in X, and X goes to this function f of X, which takes Y to distance from X to Y minus distance from the base point to Y. And the closure of X in this space is called the Horner function compactification. And so this is the Horner function boundary. So this is sort of the smallest compactification of the space for which the Boozman cocycle extends continuously to the compactification.
What is CX again?
So this is the space of continuous functions on X. So for if your space is locally compact, okay, you can always find this closure. Yeah. All these functions, so all of these functions are 0 at the base point. So
what topology?
Compact open, uniform convergence of compact sets. Yeah. But so for example, for hyperbolic space, the thing to keep in mind is for hyperbolic space with the hyperbolic metric, it's the usual visual boundary of the space. So that's something.
But you're not assuming X to be proper here, right?
Proper, yeah. Here this is proper. In this talk I won't deal with proper spaces. We'll only in most talks that I give I don't. But gamma is a proper. This is a locally finite. Cayley graphs are right. Right. So this is. So I call this the Martin compactification of gamma. And the complement of gamma here is called the Martin boundary.
Where do the continuous functions come in? I'm sorry.
Where do the continuous functions come in? So first of all, in the application here, continuous is not a big assumption because it's a discrete set. But this is a continuous function.
Yeah.
So you look at the image. So this is an embedding of X, of the space X into the space of a continuous function. And you look at the closure of the image of X in this embedding.
So it's those continuous functions that you're looking at.
Yeah, that's right. Right. So And again, sort of an important theme in studying random walks and groups is to relate the Martin boundary of a group to some known geometric boundary, like some visual boundary, something like that. By the way, the Martin boundary, it has the property that almost every sample path of the random walk converges to the boundary, converges to a point in the boundary. And it's sort of the most intrinsic way to construct such a space.
Topologically, a compact topological space.
Yeah.
Poisson boundary.
I mean, well, the Poisson boundary is not a topological. Yes, I don't want to talk about the Poisson boundary much, but the Martin boundary is always a topological model for the Poisson boundary. But saying that something or other is the Poisson boundary of a group is a much weaker statement than saying it's the Martin boundary. Okay. So, right, so when is the Martin boundary known? So if gamma is Zn and sorry? It's not going to matter now.
It's not going to matter, okay.
Well, yeah, it's still going to be well. I'll say it. It doesn't really matter. But, yeah, and mu is centered, which means then the Martin boundary is a single point. In fact, if it's centered, even assuming gamma, so actually the same is true if yeah, and I want to assume too, yeah, gamma is nilpotent. Sorry, I want to say here with finite support. It's actually weaker than that. But so this is a theorem of Margulis in this generality. If mu is not centered, then the Martin boundary is equivalently homeomorphic to an n-1 dimensional sphere. So this falls into the realm of probability of like actual probability. So now this more pertinent example to us gamma hyperbolic and mu has finite support. Then the Martin boundary is homeomorphic to the Gromov boundary of the group. So this is a theorem of Ancona. Actually, this finite support condition can be relaxed to having a super exponential first moment. So super exponential moment. And what does this mean? It means that for all c greater than 1, the sum is finite. So everything I say is going to be true. This is the assumption. The working assumption that we have is always this, but you can just keep finite support in mind. OK, so this is Theorem of Encana. And the key sort of result, so the key technical tool he uses to prove this theorem, so this is called the Ancona inequality. So it relates the green metric and the group to the word metric. So if x, y, and z and gamma are along a word geodesic, so a geodesic in the Cayley graph, in that particular order, then this green distance between x and z up to a additive constant is greater than the sum of the green distances from y to z, between y and z. So roughly, the green metric is additive along word geodesics. And you can actually use this to show it's not too hard to see that for hyperbolic group, this implies that the green metric is also Gromov hyperbolic. Right. So we wanted to generalize this result beyond hyperbolic groups. So by the way, the green metric for measures of finite support or even super exponential first moment, the green metric is always quasi-asymmetric to a word metric. But the green metric, despite being Gromov hyperbolic, is not geodesic. So it doesn't follow immediate. Yes. So yeah.
So when you say that it's hyperbolic, you mean in terms of
the Gromov product? Yeah. It's actually almost so you have these almost geodesics, which are geodesics up to additive constants. So you can define in terms of quasi-geodesic triangles and things like that. But yeah. Okay. So we wanted to extend it to so. Right. So, well, I shouldn't claim us because we didn't come up with the definition of relatively hyperbolic groups. It's Gromov. But yeah. So what's a relatively hyperbolic group? So suppose gamma acts on a compact space Z by homeomorphisms. So the action of gamma on Z is said a convergence action. So it's said to be a convergence action if it's discrete on triples of distinct points. So a point in Z is said to be conical for the action if there exists alpha and beta distinct points in Z and a sequence Gn in Z, a sequence Gn in gamma with Gn Xi converging to alpha and Gn of anything else converging to beta. So this is not for people who do hyperbolic geometry, this is not the first definition of conical you can think of, but I'll connect it to something more familiar in a moment. So this point is called bounded parabolic. If the stabilizer is infinite, and gamma of C is infinite, and the stabilizer acts cocompactly on Z minus assume this action is also minimal, so orbits are dense for now. Yes, on Z minus this point. Okay, and this action is called geometrically finite if every point in Z is either conical or bounded parabolic. Okay. So if gamma is a collection, if omega is a collection of subgroups of gamma, the pair gamma of omega is said to be relatively hyperbolic if there exists a compact Hausdorff space Z such that gamma, the action of gamma in Z is a geometrically finite convergence action. And the stabilizers of parabolic points in Z are exactly elements of omega. So in this case, so this space is unique up to equivariant homeomorphism, and you can always realize it. So yeah, so Bowditch showed this space is unique up to equivariant homeomorphism, and Yaman showed that you can take, in this case, you can always take Z to be the boundary of some proper hyperbolic space X. So this is proper Gromov hyperbolic space. On which gamma acts by symmetries. And then you can take the definition of conical then is equivalent to if you take a geodesic in that direction, it intersects yeah, it's going to intersect bounded neighborhood of the orbit infinitely many times. Okay, so time flies. So this is myself, Gerasimov, Potihilo Yang. So suppose you have yeah, so X is a proper Gromov hyperbolic space, and this is geometrically finite action. So geometrically finite, so it means the action and the boundary is geometrically finite. Then for all C, yeah, and so mu is a measure at gamma with super exponential first moment. Okay, so what do we conclude? Then for all C, there exists a D such that if G1, G2, and G3 are in gamma, and so you fix a base point O in X, and if the geodesic from G1O to G3O is not very far from G2O, so if this distance is less than C, then the green distance from X to Y plus the green distance plus Y to Z is greater than, less than the green distance, G1, G2 is less plus the green distance from G2 to G3 is less than or equal to the green distance from G1 to G3 plus D. So the same conclusion as in these Ancona inequalities. And so we have a corollary about the Martin boundary. So there is an equivariant continuous surjection from the Martin boundary of gamma to the boundary of x, and the preimage of a conical point is a singleton. So you can get this. This is not completely straightforward, but you derive this from that version of Ancona inequality. So what do preimages of parabolic points look like? So what about parabolic points? So in general, we don't know, but so this is Dusala, myself, Gerasimov, and Patihailo. So under the additional assumption that under the additional assumption that the parabolic subgroups are virtually abelian, so we can actually completely describe the Martin boundary of this group. So say you have this map pi from the Martin boundary to the boundary of the space. So if this is a parabolic point and the stabilizer is virtually Zn, then by inverse of then the preimage of this point is homeomorphic to the sphere of dimension n-1. So in particular, this has a very nice description when gamma is a lattice in Hn. So suppose gamma is non-uniform lattice in real hyperbolic space. So you can create something that's called the truncated space or neutered space by deleting from Hn this joint equivariant family of horoballs centered at centered at parabolic points of gamma. So let y I will we do it by deleting equivariant disjoint family of horoballs centered parabolic points. Okay, so what do we know? So Y is ket 0. It's a ket 0 space. And the group acts on Y co-compactly. So in this case, our theorem says that the Martin boundary of gamma is the visual boundary of Y, the ket0 boundary of Y. So in particular, when n equals 2, or sorry, when n equals 3, this Martin boundary is homeomorphic to the Sierpinski carpet.
Why does this theorem say that? Because I thought that the space X here is the original Hn.
Yes, the space X is originally Hn. The preimage, but this map is not a homeomorphism.
So you explode some points to circle.
That's right. You explode some points to circle. You explode parabolic points to spheres of the right dimension. So here they're circles. Yeah.
And you get this ket0 boundary of Y. Is that what you get?
Yeah. That's. I mean, yeah. You have to be careful with topology, but this is exactly what you will get. In fact, you can describe exactly, I don't want to write everything down, but exactly like a sequence, so it's characterized as follows, like a sequence of points in the group converges to a point in the Martin boundary if one of the two happens. Either you converge to a conical point in the boundary of X, or you converge to a parabolic point in the boundary of X, and the nearest point projections of your group elements to the parabolic subgroup converge in the visual boundary of that subgroup. And this is sort of, if you unravel the definition, this is exactly what happens here.
I see. Okay.
Okay, so I have 8 minutes, but I want to talk about sort of our methods, because our methods, so first of all, this has a lot of dynamical and sort of, a lot of probabilistic applications that I won't talk about because I only have 50 minutes. But I want to talk about our methods. So they're completely combinatorial, and they don't really use hyperbolic geometry, except some old black boxes. So they deal with something called the Floyd metric. Okay, so given a Cayley graph, okay, so you have a Cayley graph of gamma. And so let f be a function in the reals which is integrable and decays at most exponentially. So you fix a base point. So you can rescale the Cayley graph by declaring the length of an edge E in the Cayley graph, or maybe I don't want to call it, declare the length of a length E in the Cayley graph to be, f of the distance of the word distance from E to the base point. So edges far away have small lengths. So because you assume this function is integrable, so first of all, this induces some path metric on gamma. Right, so this induces this path metric on gamma, and it has finite diameter because of this condition. And the completion is called the Floyd compactification. Right. So, and you have a metric on it, so depending on the base point, called the Floyd metric. So, on the completion. So, for most groups, this Floyd compactification is trivial, but for relatively hyperbolic groups, Gerasimov proved that it equivariantly covers this Bowditch boundary, this boundary of the hyperbolic space in which gamma acts properly geometrically, well, in which it acts geometrically finitely, and that the preimage of any conical point is a single point. And actually, if all the parabolic subgroups are are amenable, then it's a homeomorphism. Yeah, if they're amenable and non-virtually cyclic, then it's a homeomorphism. Okay, so how to rephrase this Ancona inequality? So first, so I'm going to remove, not write all the quantifiers, but so if you have points G1, G2, and G3, and the G2 is close to a geodesic between G1 and G3, then the Floyd distance between G1 and, the Floyd distance with base point G2 between G1 and G3 is bounded below by something. So these Ancona inequalities can be rephrased as follows. So if x, y, and z are in the group, and the Floyd distance based at y between x and z is greater than delta, then you have this reverse triangle inequality. Where C depends only on delta. And corollary there exists a continuous equivariant map from Martin boundary to Floyd boundary, and the preimage of a conical point is a singleton. Okay, so I'm out of time. I just want to mention at least one dynamical consequence. So if you have a geometrically finite action in a proper Gromov hyperbolic space, and you also assume it's not convex or compact, there's two ways to construct measures in the boundary corresponding to two ways of measuring over the group. One is the Patterson-Sullivan measure that you get by measuring over ball averages, which in the case of lattices in HN or in symmetric spaces is Lebesgue measure. Another way is the stationary measure for the random walk, which you get by taking limits of convolutions of the random walk. So we have a theorem. So using this technology, we prove that if you have finite support random walk, or even super exponential support, super exponential moment random walk, and the action is geometrically finite but not convex or compact, then the Patterson-Sullivan measure and the stationary measure are singular. Okay, so I'll finish.
Okay, any questions?
Maybe I have a question.
Yeah.
So can you prove that hyperbolic groups are cap minus 1?
No. But this is yes, but this is a very relevant question because this right. So the Boozman function, if you take a hyperbolic group and you take the word metric, the Boozman functions for the word metric do not extend continuously to the boundary, to the Gromov boundary. And this is something that is satisfied for cat minus 1 metrics. And this green metric, for this green metric, the Boozman functions do extend continuously to the boundary.
Well, yeah.
By the question. Yes, it justifies the question. So the answer, yes, the answer is still no, but you can do a lot of things with this green metric that you would want to do with actions on cat minus 1 spaces. Yeah, but
so I had a question over here. So where does the boundary of X fit into this picture? So there is a map between the Martin boundary and Floyd boundary, and you have the corollary there.
So you mean the relation between the Floyd boundary and the?
No, I mean, is there a map?
Is there a map?
I mean, so you also have this other map over there. So
yes.
How does that fit?
So how do you right? So Gerasimov.
How does it fit with that map?
Right. So Gerasimov proved that for a suitable Floyd function, you have a map from the Floyd boundary to the Bowditch boundary, to this boundary of X.
From the Floyd boundary. So
yeah.
It goes further.
Yeah. So Gerasimov constructed the map from the Floyd boundary to the boundary of X, and we constructed somehow combinatorially the map from the from the Martin boundary to the Floyd boundary. So the composition, and it's both maps are 1-to-1 where they need to be. So it's.
My other question about your model of logical helicity. So for this definition of geometric finiteness, parabolic subgroups are defined generated.
In this definition, they do not have to be, but if they are, this is equivalent to Farb's definition.
I see. But so this definition does not require them.
That's right. Yeah.
All right. Any other questions? Okay. Thank you very much.